Hey everyone, and welcome back to this Ansys simulation software tutorial series. Today is going to be our last FEA example video in this series, so make sure to pay attention and pick up whatever you can. We're going to be simulating on an example geometry for what Trinity's lower airframe might look like, so let's get to it. We'll start, of course, by opening Ansys Workbench up. There it is. And drag a static structural into the system. We'll name this Trinity lower airframe. Trinity, of course, being our Liberty Rocketry competition rocket for the 2025 Spaceport America competition. We won't need structural steel because we're going to be using some custom carbon fiber data that our team derived for the specific plates that we were using. Custom carbon fiber data for Trinity. Let's capitalize that because you have to have good English. We can close these, and I have a photo right here for the materials data, so we can just enter it from here. Let's drag density and orthotropic elasticity and tensile yield strength into the properties. Before I start entering orthotropic elasticity, I want to show you that if you use isotropic elasticity and you enter Young's modulus of something and then a Poisson's ratio, you cannot edit the other two. It automatically derives these for you. So you can change what you want it to derive and what you want to enter using this drop down, but you cannot change the things that have been derived. If you want to get around this, you can usually get away by entering the same value for Young's modulus and Poisson's ratio and shear modulus in each of the three axis directions. And then, while Ansys will, for example, derive for you, you can still change this to whatever you want. So let's delete that and let's start over. Density is at 1.6 and grams per cubic centimeter. And this was deliberate. This is your reminder here. You should have seen just there, when I changed this to grams per cubic centimeter, it changed density, the value, to 0.0016. That is because Ansys is nice and will auto convert your units when your value when you change the units. So what you should do is change the units first and then change the value. So let's go ahead and set all of our units before we finish entering our values. Awesome. Young's modulus x direction 0.118, and use enter here so you don't have to use your mouse, because as a rule of thumb, when you're using computers, the more you can keep your fingers on the keyboard, the faster you can go. And that's automatically derived and that matches up. And if you want to change this to gigapascals just to see more easily, that is nice and useful. And this is 395.5. And there we go. Now for the geometry, this is linked in the description, so you can download this and use this for your project as you follow along. There's the geometry. Now let's double click model. And their Ansys Mechanical has started up, but the buttons are not responding. There, the buttons are responding, so we know it's started up. Here is our geometry. That is roughly what the Trinity lower airframe looks like. Again, I say roughly. This is not the actual lower airframe. That data is proprietary to Liberty Rocketry. So this is just a rough estimate. However, if you become a platinum sponsor for Liberty Rocketry, I believe you do get access to the CAD file, so you may consider doing that. We're going to be applying forces on the fins. So what would happen if the ground hit the fins like this because the rocket landed coming in this direction? Or what would happen, conversely, if someone stood on the fins with their body weight? How much would the fins bend? Would they be able to survive? This is something that is actually going to happen at the Spaceport America competition. One of the judges will stand on our fins. So for factor of safety, we're going to say for this simulation that the judge weighs 200 pounds, which is approximately equal to 888 newtons. So we will be using that amount of force. Before we do that, you'll notice that the z-axis is parallel to this fin. So this fin is pointing in the negative z-axis. So we will be applying our forces with this fin straight up and fixed, and we will be applying our forces to these fins. And since the forces will be parallel to the negative z-axis, that makes our life easier if we want to enter things as components and we don't want to enter forces as vectors. So let's go ahead and set this as, excuse me, Ansys. We're going to try again to set this. That is our new isotropic view. So if we ever want to return to that, or isometric view, excuse me. There you have it. So geometry. It's only one body, so it's fine if we just assign this directly. Carbon fiber. Then for mesh, we need to decide on a mesh sizing. I made this geometry so that each wall is 10 millimeters thick because I didn't want it to have to require a ton of tiny little particles, tiny little elements that would require way too much processing power. And you can see that using the measurement little display right here. It's 10 millimeters wide. And if we go to the side of this, we can see it as well is about 10 millimeters wide. So since we want two elements across the thickness of any given wall when we're using Ansys simulations, we would want a 5 millimeter mesh. So let's insert and go to sizing, geometry. We'll be using this body, apply, element size 5 millimeters, and click generate. And there Ansys has finished meshing. So let's take a look at our mesh. What a beautiful mesh. Lots of nice little particles. This should simulate very nicely. So I also want to show you the auto mesh because that is very useful for getting quick results. And I want to show you the difference between different mesh qualities. So let's insert another sizing and apply the same geometry. And we're going to leave the element size as the default. So to prevent this from conflicting by having two mesh sizings, we're going to press F2 here and name this fine mesh. And body sizing 2 will be renamed as auto mesh. I don't think auto mesh is the official term for it, but it's pretty descriptive. So we're going to right click and suppress the fine mesh. And now we're going to generate the mesh again, and that should be practically instantaneous. If you look at this mesh, this is what Ansys will automatically give you if you didn't insert a sizing and just hit generate. You can see the elements are a lot bigger and they're generally a lot flatter. This is not going to give us as accurate results as our fine mesh over here. And to see that quantitatively instead of qualitatively, you can go to mesh and then click the mesh metrics display, click the drop down here and click element quality. This is going to pull up the element quality graph where the number of elements is displayed on the y-axis and their element metrics, which in this case is element quality, is displayed across the x-axis. You can click on these bars. If you hold down, you will see the number on the left is the element quality, which matches up because that's right between 0.4 and 0.5, and the number of elements of that kind, so this would be 1,320. There's a normal distribution, give or take, around this bar. So the average mesh quality is going to be something like 0.45. If you click this and you zoom in, you can see that these elements are pretty wide. They're flat and they're not the same all around. They're not regular shapes. If you expand this so that these bars are easier to click, and you click this, which is further up and is higher quality, you can see that the very few elements of this kind, I'm counting 6, 7, 8, 9, no, that's wrong, 10. I'm counting 10. Then you can see that these are much more regular. They're not perfectly regular, but their angles are a lot closer to each other, and their side lengths are all a lot closer to each other. They're generally more of a regular pyramid shape and less of a flat and skewed shape, which means that these elements are better than these elements. And if we go down here, we can see these are really, really flat and really, really not great. So these are going to give us worse results, the more of them that there are, than these are, and these are going to give us worse results than these are. So let's unsuppress this and suppress this, and we're going to have to click generate again. We can see these elements are already looking a lot better since there are multiple of them across the thickness of this wall. They don't have to be flat and long. And we can see that our normal distribution centers around 0.88 here instead of around 0.45, which is somewhere around here. If we click this, we can see that there are a few of these flat and long elements that are not as great for the simulation, but relative to the volume of our geometry, these are pretty sparse. We look at some of the higher quality elements, there are a bunch of these all over the rocket. And if we zoom in, let's see if we can find one that's kind of isolated here on the tip. There, how about this one? This almost looks like a perfect little triangular pyramid with side lengths and side angles being very, very close together. If we want to see something further up here, we can go to Controls and increase the number of bars to 20 and click Update Y-axis, and that will show more bars, giving us more selection. If we wanted to, we could change this to 50, which is probably going to lag the computer, but even still. Now we can choose elements that are 0.991 quality. Very, very good, nice little triangular pyramids. These are going to simulate very well. Much better than something down here like this, which is very flat. So this mesh, the fine mesh, is the ideal, and this is what we would want to use for our final results. But for the sake of speed for this video, so you don't have to sit and watch the video or watch something else while your computer is loading the mesh, we're going to delete the fine mesh, and we're going to delete the auto mesh as well, and just let Ansys do whatever it wants by clicking generate here. So this is what we will be using for this video. Just keep in mind that this is not the ideal. So we want to simulate our fins, don't we? Yes, we do. Let's close these two so we have a better view of our geometry, and switch back to our isometric view. And we are going to first, of course, insert a support. fixed support. We're going to be fixing the surface of our upper fin. We can't fix this because that's all one body. Click apply, and that is good. Now we are going to insert a force upwards on our fins. Let me rotate the view around here a little bit. We're going to select edge, then this edge, hold control, and this edge, click apply, define the direction using this, and make sure that that is pointing up, and click apply, and the magnitude is going to be 888, which is an estimate, but it's good enough. And for solution, we are going to insert total deformation and equivalent von Mises stress. So we could click solve, and this will give us a solution. But in this tutorial, we want to cover a couple of other different scenarios here as well, just for fun and to get a little bit more experience. So here we're going to be using multiple static structurals in the same simulation, which is something you might not have known that you can do until this point. So to do this, we're going to click Analysis and then click Static Structural. First, let's rename the static structural. Click this, press F2. We're going to name this fins up. This will be F2 fins together. And to speed up our simulation of what would happen if these forces were applied this way, where the fins are coming straight together, we're just going to grab our fixed support and drag it over here. Total deformation, equivalent stress, and we are going to drag our force as well. This, of course, would make everything exactly the same, but we are going to change our force. Before I do that, I'm going to show you what this looks like in Workbench. You can see we have a second static structural showing up here, the B static structural, which would be this one right here. Here's the A and here's the B. The names have not changed, but these two are now separate and they both exist together. And engineering data, geometry, and model are being shared between them. That would be all of these. So these two are both going to be using the same mesh, geometry, and materials setup, while they'll be using different setup, solution, and results. So that's what the difference looks like in Workbench. You will note, however, that if you create another system, it is not possible to add a static structural from Workbench because while you can hook up engineering data and geometry, you cannot hook up model like this one has. There may be a way to do it. If there is, though, I do not know it at the moment. So, to change force, we're going to rename this force to upward force. And we're going to name this one left fin force. And we are going to duplicate it and name this one right fin force. Now, to remove the right fin from our left fin force, we can actually select this and then use the little minus. Now you'll see that our geometry has changed to say only one edge instead of two, and if we click it, only the left turns green, the right one does not, so we know that we're good. Our direction, we're going to have to define using this, or we could, yeah, we're going to use that. And now the left fin will be pushed to the right. The right fin, we're going to do the same thing as before. We're going to select this and remove that from geometry. The arrow will stay over here, but only this is having a force applied to it, so don't worry about that. And we're going to define this one by components. Since we decided that we wanted this fin to be parallel to the z-axis, it's easy to apply a force directly this way. We can just type in a positive x force of 444, which is half of 888. And we should change this one as well to 444 newtons. So now we have our left fin force this way and our right fin force this way, both on opposite fins. And we could click solve, but we're actually going to add another simulation system here. So instead of using this button and then dragging things over, we're just going to right click fins up and click duplicate. And click the plus, and you can see that everything has been copied here. Let's change this to fins down, and change this to downward force, and change the direction of our downward force using this edge. Now we're going to have a fins down force, a left and right force, and an upward force. And that is all that we're going to be simulating in this video. And since we're using a coarse mesh, this should go pretty fast. So let's go ahead and solve it. If we click fins up, or something under fins up, and we click solve, it's going to show a green lightning bolt for all of the things under fins up. And it is going to solve everything, including an under the tree item that we selected. Oh dear. An unknown error has occurred. Well, let's troubleshoot. I'm going to reduce my cores to 4 and see if that solves it. Alright, it's time for some unscheduled troubleshooting. Alright, so I'm reading through here and it's saying something about Poisson's ratio and material type 1 and orthotropic, and it's missing something. So I'm guessing that the problem is our engineering data. Alrighty, a bit of a time loop here. I just tried to solve the model and it didn't work. Ansys was throwing a fit at me until I went back to the engineering data and I changed this from 32 to 30. So just change that and let's get on with the video. So what I was trying to say before everything happened is that if you click this and then you click the solve button, it's going to solve this item and everything attached under that item in the tree. So if we click fins up and click solve, it's going to solve for fins up, but it's not going to solve for fins together, and it's not going to solve for fins down. However, if you click above this tree item, like model for example, and you click solve, it is going to solve everything under model, which includes fins together and fins down, and fins up, but that's already been solved. So now we just have to wait for it to solve that, and then it will automatically go to this one and start solving that one as well. And there you go. Now it has solved everything. And we can see our total deformation for fins up is as we expected. It is bending the fins upward. And our total deformation here, the fins aren't together. And the total deformation here also shows the fins together. So let's interpret our results a bit here. This one is pretty straightforward. The fins are going up. This one shows the fins going down, and this one does too, but it's kind of odd that the total deformation for fins together and fins down is the same. Why is that? Why is that happening? Well, it's important to remember that the visuals in Ansys are not necessarily accurate because they are mostly for just gathering a general interpretation and not for precision, because things are scaled. If you look, the total deformation here at a maximum is 1.036, but here it's 1.659, so we should expect a variance in how much it bends. But the scale here is 56, Well, the scale here is 35, and it's doing this to display it in a more user-friendly format, I suppose. So we can fix this by either going to true scale, which barely shows anything and isn't that helpful, or we can just type in our own scale. Let's do 50. Now that will preserve the scale across the two of them, and we can see that the deformation is indeed different on both of them, as well as up here. So as we would expect, our maximum deformation occurs at the tips of the fins, and the maximum stress is occurring around here. Now, it's not good to have this much of a gradient in a single element. We want gradients to occur over multiple elements for more precision. We're seeing a maximum of around 15.932 megapascals, which is significantly lower than the tensile yield strength, maybe a factor of 20 or so. And that's good, but before we're too certain that this is the case, we're going to want to refine the mesh and run the simulation again. But we're not going to do that in this video because that is going to take too long. So there is your rundown of how to have multiple analysis systems running together at the same time, and how to copy and paste things, and how to do a little bit more with meshing. And I hope you learned something of the troubleshooting process from our inadvertent troubleshooting session that happened uh, in the video. Alrighty, that wraps it up for this video. I hope you gained something and that you're now a little bit more competent with how to use Ansys simulation software. As always, may the Lord bless your engineering. Come visit us at LU sometime and move on to the next video, which will be about miscellaneous tips and common errors when using Ansys FEA.